Picture a universe with nothing left in it. No stars burning, no galaxies turning. Just black, silent space stretching in every direction, farther than light itself can cross. And yet, somewhere in that emptiness, one thing still exists. Not a star, not a planet. A black hole. The last surviving structure in all of existence, holding the final scraps of mass the universe has left. For unimaginable stretches of time, it simply sits there, patient and unmoving. But patience has a limit. Eventually, even this, the darkest, most permanent object ever formed, begins to unravel. And what happens next may decide whether the universe truly ends or simply begins again. For decades, black holes had a simple reputation: perfect prisons, cross the boundary known as the event horizon, and there's no coming back. Not for matter, not even for light. It seemed like the one rule the universe never broke. Then, in 1974, physicist Stephen Hawking found a crack in that rule. He showed that black holes aren't quite as sealed as they appear. Right at the edge of the event horizon, strange quantum behavior takes place, the kind of behavior that doesn't play by the tidy laws of classical physics. And because of it, black holes leak. Slowly, faintly, constantly, they release energy out into space. This isn't matter escaping from somewhere deep inside. Nothing is tunneling its way out from the core. Instead, the effect comes from how quantum fields behave in the warped, curved space-time that surrounds every black hole. Near the horizon, the curvature is extreme enough to generate real, measurable radiation, energy conjured from the geometry of space itself. It's an almost poetic contradiction. The object built to trap everything, even light, turns out to be quietly glowing at its edges. And that faint glow, technically known as Hawking radiation, is the very first hint that a black hole's darkness was never meant to be eternal. A slow bleed that turns into a sprint. Here's where the physics gets dangerous for the black hole itself. Every particle of Hawking radiation that escapes carries energy away with it, and that energy has to come from somewhere. It comes directly from the black hole's own mass. So with every emission, the black hole gets a little lighter, and as it loses mass, its event horizon physically shrinks. That shrinking triggers the next step in the chain. A smaller black hole runs hotter than a larger one. It's a strange, almost backwards rule of black hole physics. Shrink the object, and its temperature climbs. A hotter black hole doesn't radiate at the same gentle pace. It radiates faster, which means it loses even more mass, which makes it smaller still, which makes it hotter again. Around and around this cycle spins, each loop feeding the next. For nearly the black hole's entire existence, this process crawls along at a barely detectable pace. But as the end approaches, that slow bleed transforms into something else entirely. A runaway sprint toward total evaporation. Why nothing is evaporating around us right now. Given all that, you might wonder, should we be worried? Are black holes quietly dissolving somewhere in our galaxy at this very moment? The honest answer is no, not even close. The black holes we know about today are extraordinarily cold, and this evaporation process only becomes dramatic on timescales that dwarf the current age of the universe. A black hole with roughly the mass of our sun would take somewhere around 10 to the power of 64 years just to fully evaporate, a number so large it makes the universe's current age look like a single second. There's another reason today's black holes aren't shrinking. They're not isolated. They sit inside a universe still filled with background radiation warmer than they are, which means they currently absorb more energy than they lose. Right now, black holes are still being fed. Their slow death hasn't even begun. The black hole era. But that protection won't last forever. As the universe keeps expanding, the background radiation surrounding every black hole will grow steadily colder. Eventually, a tipping point arrives, the moment when a black hole starts losing more energy through Hawking radiation than it absorbs from its surroundings. That's when the balance shifts for good, and the slow countdown to evaporation truly begins. By then, almost everything else in the cosmos will already be gone. The last stars will have burned out long ago, and no new ones will be forming to replace them. Galaxies will have drifted apart, pulled farther by the relentless expansion of space, until nothing recognizable as a galaxy remains. In this distant chapter, sometimes called the black hole era, these ancient objects become the last major structures left standing in an otherwise empty universe. Smaller black holes go first, fading out relatively quickly once their time comes. The true giants, the supermassive black holes that once anchored entire galaxies, hold on far longer, potentially surviving for something like 10 to the power of 100 years. By the time even they begin to fade, the universe will be an almost featureless black canvas. No galaxies, no starlight, nothing nearby. Each remaining black hole exists in near total isolation, separated from any other by oceans of empty, expanding space. Eventually, only one black hole remains, the final object in an otherwise empty universe. For nearly its entire existence, its decline is almost imperceptibly slow, a barely there glow fading across unimaginable stretches of time. But as it approaches the very end, the same runaway process from earlier kicks in with full force. Mass loss accelerates, temperature spikes. The emission of Hawking radiation intensifies into one final brief surge, then the last event horizon in the universe disappears. It's tempting to imagine this moment as explosive, maybe even the spark of a new Big Bang. It isn't. The energy released doesn't ignite anything new. It simply spreads outward into a universe that's already unfathomably vast, thinning out and cooling as space continues its endless expansion. The final black hole doesn't restart the cosmos. It simply erases the last object still holding matter together in one place. What's left afterward isn't structure. It's scattered particles and fading radiation drifting through darkness with nothing left to hold onto. That sounds like a final absolute ending. But not every physicist agrees the story stops there. One provocative theory suggests the universe's emptiest, most distant future might not be the end at all. It might be a beginning in disguise. The idea comes from physicist Roger Penrose through a framework known as conformal cyclic cosmology. In this model, the universe doesn't have just one birth and one death. Instead, cosmic history unfolds as an endless sequence of cycles, each one called an eon. Every eon starts out looking like a Big Bang, expands for almost incomprehensible lengths of time, and eventually cools into near total emptiness. Here's the twist. That empty ending is mathematically linked to the explosive beginning of the next eon. But there's a catch. As long as massive objects like black holes still exist, the universe has measurable scale. Size, mass, distance. And those properties block any clean transition into a new beginning. For Penrose's idea to work, something has to remove every last one of those massive structures first. This is where Hawking radiation becomes essential to Penrose's model. If every black hole eventually evaporates completely, the universe loses its last remaining concentrations of mass. What's left behind is dominated by radiation, and radiation, unlike matter, has no fixed scale. Under certain mathematical transformations, an infinitely expanded universe filled only with radiation can be reinterpreted as the tightly compressed starting point of a brand new eon. In this framework, the old universe never actually collapses. Its far future simply gets rescaled into someone else's Big Bang. A 2025 paper by Penrose and physicist Christoph Meissner pushed this idea even further, describing specific locations called Hawking points, theoretical remnants marking where dominant black holes in a previous eon underwent their final evaporation. According to the theory, these bursts could leave faint circular imprints inside the cosmic microwave background, the ancient radiation left over from our own universe's infancy. It's a striking possibility. Certain patterns in the sky might not have originated with our Big Bang at all. They could be echoes of black holes that died in a universe before ours, but this remains unconfirmed. Researchers combing through data from the Planck and WMAP missions have so far found no statistically significant evidence supporting these Hawking points. So, where does that leave us? The confirmed part of this story is solid. Hawking radiation is real, and it guarantees that even the most permanent-looking objects in the universe, black holes, cannot last forever. Given enough time, they evaporate completely. The speculative part is Penrose's idea that this evaporation might also set the stage for an entirely new universe to begin. It's a compelling theory, but it isn't proof. Hawking radiation doesn't confirm that our universe had a predecessor, and it doesn't guarantee another one follows after ours. What it does offer is something quieter, but no less remarkable. A real physical mechanism by which the darkest, most enduring structures in existence can finally disappear. And maybe, just maybe, a way for one universe's ending to become compatible with another one's start.